Hello?
Hello.
Hello, Professor Aurich. Nice to
So,
meet you.
yeah,
Okay.
nice to meet you again. I hope you can hear me. So everything seems to work perfectly.
Yes, Zoom is quite reliable, I have to say. Mm.
I'm just checking. I cannot show slides yet.
Okay, just let me see.
Let me send you. I can send a request.
Allow, yes. And unfortunately, today is Chinese New Year, and so we will have less participants. I didn't realize this. Uh, mm. We have many Chinese in the staff.
Okay. So they have. Uh,
And also in the webinars, we have also many people from China. Because this is a time slot
yeah,
that goes well for, let me say,
yeah,
3 minutes,
yeah.
which
Let
was
me try if I can
what?
share. You
Yes,
see my slides now?
I can see.
Okay, so I stop it and can do this later on just to check that it works.
Okay, I can see. Yes, very well. I see your CV. So you, like all the professors in Germany, you have an experience in industry.
Yeah,
Right?
yeah, it's quite a time ago, but I was 7 years at
Uh,
Mercedes,
yes.
both in the passenger car and then later in the truck division, which is now
Uh,
independent company.
yeah. uh, uh, and now let me see Sylvia if it is joining or not. Generally, they join in the end.
So how many participants do you usually have in the meeting?
Oh, I don't know. I'm a little bit worried because we started with I think the first webinar was from Michael Greaves,
Yeah,
and we reached at around 100. Okay, so it was very successful. And then we alternated. There was Warren Power from Princeton, I don't know, around 60. And then we moved, between 30 and 50. But the last webinar was not good because we had around 20. And I'm a little bit worried today because it's after
yeah,
the
this
autumn,
is
maybe winter, and it's strange. Anyway, I'm not a webinar organizer as a professional, and so I don't know what is the best period. Yavar is joined us. He's a
Hello?
PhD. Dario
Uh,
Dario is working in the AutoTwin project. This webinar is sponsored by AutoTwin. We are in the last year of the project now. We are very very active to submit a bunch of deliverables by the end of the month.
yeah, I see. Okay, I have to do.
And the project will finish in November.
Okay, I see.
Just a few information about AutoTwin. So the goal of the project is related to circular economies, but we cannot model all the circular economies because we need, all the partners in the consortium is difficult. So a portion of the circular economy, and the main ambition is to get the data from the system, production system or inventories or product. And based on the data, we generated, let me say, the mathematical model of the discrete event simulation. And we generated 3 kinds of models, so graph model, Petrinet model, and automata model. So we have different perspectives. And then from these models, we translate, that is one of these, that we translated the mathematical model into a discrete event simulation model. And then we have what we say the digital model or the digital simulation model or the digital twin. And then we make decisions and so
Yeah,
we
yeah,
we implement the decision, we check the data, and then we check if the decision is aligned with what we see in the future, and then we go on.
Yeah, I actually looked at the homepage of the AutoTwin project the last 10 minutes before I logged in here, and I could see this, which you do with the circular economy and then the digital twins and the models. So that makes a lot of sense, I think, because circular economy without the digital twin will not work. So it's a
Yes. So we have this ambitious goal. Oh, we have also Professor Framinan from Seville University, very expert also in scales. And now people will join.
Yeah, okay. Yeah, see, we just wait for.
Yes, it makes sense also because without without a tool that we or coordinate and makes prediction, then it's difficult. We have three use cases, one on plastic recycling. So we had discrete event simulation of the plant. Another use case on battery. Here we have a product digital twin of the battery rack for energy storage. It's not on the supply chain. And then we have another use case in the healthcare sector. So the sterilization center inside the hospital that has to sterilize the medical devices coming from the surgeries. Here we are closing the loop because the loop is very short because you have the medical device, you sterilize, you bring to the surgery, they use it, and it comes back. This is the case in which we close the loop. As you listen, I'm not in a very healthy condition.
Yeah, I can hear that. That's the advantage.
I'm at home because since yesterday.
Online, yeah. So
I'm at home because it's what time is it? Okay, it's we wait another few minutes. If someone wants to ask some question to Professor Aurich, you are welcome. Erik Verbeek is from Eindhoven University, another university in the project. It is the university where process mining was, let me say, conceived. Okay. I think now in Germany you have the professor from Eindhoven that moved to Aachen, if I remember. What is Verbeek? The name of
Wil van der Aalst.
Van der Elst.
Ah, okay, yeah.
Yeah, he moved from Eindhoven to Aachen. I cannot offer a coffee. Sorry.
No, I have my drinks here. I have something.
Wait another few minutes.
Of course, that's what's still missing with Zoom, the possibility to hand over a coffee or something else to
Not
drink.
yet. When we have the drones that will be very efficient, then I can make an order. Yes, as this is a confirmation, we have no Chinese in the audience because it's the Chinese New Year. It is a proof. Okay, let me see. Okay, I think I can start introducing Professor Aurich. Sorry for my voice. Professor Aurich studying in two different universities, Leibniz University of Hanover and also in Colorado State University in US. He had first experience always in Hanover, and then he moved to for 7 years in Daimler AG in the industry. And then after the industry, joined university since 2002 in the Institute of Manufacturing Technology and Production Systems. And he has been visiting professor at University UCD, so University of California, Davis, US. And I don't talk about the different research topics his team is working on. I just leave the floor to Professor Aurich that will talk about digital twins from, let me say, from data. This is a very topic aligned with AutoTwin, and for that reason, Professor Aurich, we invited you for this talk. The floor is to you.
Yeah, thank you very much. So I already share my screen.
Sorry, maybe just a question. Can we record this webinar?
Oh, sure, yeah, no problem.
The European Union reviewers recommended us to do this.
Yeah, sure. So no problem. I mean, I sent you the slides beforehand as well. So if anyone is interested in the slides, you could also forward those. I mean, it's all published, so I think that's no problem to do. And of course, you can also record it. Yeah, so thank you very much for the introduction. I'm happy to give you this webinar or talk on digital twins in manufacturing. So I always have to say, sometimes I just talk of digital twin, but our work, our research is really digital twins in and for manufacturing. And today I'm talk about, after an introduction, about taxonomy we have proposed here to structure and also to evaluate different digital twins in manufacturing, and then as one of the very current topics, and I think that's also very fitting to the AutoTwin project, about the self-improving or self-learning digital twins and what different approaches are existing there, and how this can be carried out, self-learning digital twins. Maybe I don't have any slides for the presentation of my institute or university, but shortly we are the TU Kaiserslautern in Germany, and I'm heading here the Institute for Manufacturing Technology and Production Systems in Kaiserslautern. We have several key areas of our research. You see already technologies for manufacturing, such as milling, turning, also additive manufacturing. We do a lot of research recently. And then the production systems, which is mostly about digital production systems and digitalization of the production systems. And of course, their digital twin is one of the bases to do this. But we also have a lot of work right now about machine learning, also about application of quantum computing for industrial production and for production planning and control. So I think in the production systems area, there are a lot of quite exciting current research topics. And one of them are digital twins. And I'm going to talk about that today, but also when we come to the self-learning, a little bit related to this differentiation. Do we have physical models or do we have data-based models as generated by machine learning? So with that, I have a brief overview. I give a little bit introduction and motivation and what are digital twins. I think you all know this, but as there are some different definitions still existing, and especially when we look into digital twins for manufacturing, I use this so we have the same understanding and the same common ground of what is it I'm talking about. Then I'll talk a little bit about possibilities, how a digital twin structures and implemented. Before I come to the two main parts of my talk, one is proposed taxonomy for digital twin applications in manufacturing, and then about self-improvement or self-learning for digital twins in manufacturing. Before I come to summary and discussion, there also be a use case. We did a lot of research in the last 3-4 years here in Kaiserslautern, and then I have a short summary, and then we have time for questions and discussions. Okay, let me go to the introduction. Of course, you all know that. I think digital twins, of course, they extend the physical manufacturing system connected to the digital world. We all know they are key enablers for several things we want to do right now. One is for Industry 4.0, like the digitalization of manufacturing and the processes and business models around it. Of course, a digital twin is absolutely necessary, so there's a key enabler there. Also allowing optimization of manufacturing processes, different levels of the manufacturing system. When I talk about enablers, I could also mention here circular economy. Digital twins are certainly one of the key enablers for circular economy. But then manufacturing or remanufacturing is, of course, only part of the application. So why do we do this? Of course, if you look in companies, it's always cost, time, quality. Still, we want to improve, maybe also flexibility or sustainability of a manufacturing process. So such key performance indicators, the KPIs, very often need a digital twin to get the best ways to improve them. So the questions which are then remain, and I will talk about some of those in this webinar, are how are digital twin structures? What benefits can be achieved when using digital twins from manufacturing? What are challenges and difficulties which can come up during implementation? Then the question, how can we, since we have, it's also application dependent and also dependent on what are the purposes of the digital twin. So there are different implementations of digital twins in manufacturing, I think in other areas as well. So the question is, how can these be classified to make them easier comparable and to select the best one for each purpose? So that's about this taxonomy. And then the question, how can manufacturing system benefit from a self-learning digital twin? Why is that a current research direction? Why are so many people interested in that? And then, of course, how can these self-learning digital twins be implemented? So these are the questions I'm going to talk in about the next, I think, like 45 minutes. And then we still have good time for discussion and questions. So a little bit staying with the introduction. If you look, the concept of digital twins is now a little older than 20 years. The first mentioned in literature we find around 2003, and this is taking from actually from a reference and publication from Fai Tao, I think, from Beihang University. Many of you know him. So the concept first mentioned, then there was like the first 7-8 years an exploration phase before the digital twin concepts got better and better in this incubation stage in the next 3-4 years. And since then, since about 10 years ago, we see a very fast growth actually in digital twin applications. There are more and more areas where digital twins are applied. I mean, they come mostly from product design and in engineering, mechanical engineering product designs, but we apply them in manufacturing. That's what we do, but we also find digital twins in civil engineering of buildings, of cities. NVIDIA, Jensen Huang, in one of his recent talks, talked about a digital twin of the world. But if you look in more detail, it's mostly about weather forecasts and meteorology and climate forecasts at the moment. So we have many, many applications of digital twins being defined and implemented right now. So let me look a little bit in the definitions. This is taken from a publication by Wilfried Sien and Kritzinger. And I think this is very important to also to have the same basis of what we're talking about, because even though I think this, I explain that in a second, what the slide shows is quite common understanding by now. Still, Sometimes I see also in talks, in conferences, that the terms are not really used in a clear distinction. These terms, digital model, digital shadow, which we also often find, and digital twin. If I look at the definition by Kritzinger and Zien, then it's really, of course, also in a digital model, we have a physical object and a digital representation of that object. But there's no automated data flow between physical object and digital object in no direction. There may be manual data flow, and if digital object can be used to better understand the behavior of the physical object, but there's no direct data flow. Then if we talk about the digital shadow, then we already have an automated data flow from the physical object to the digital object. So that means the digital object is kind of shadowing the physical object. It always represents what's going on in the physical object, any changes. So you can always look into the digital object and see how did it change, and you know how the physical object changed. But there's no data going from the digital object to the physical object in the sense of controlling it, having automated control, and having an influence on the physical object. So if you think of that in terms of a factory, then the digital shadow is just a virtual representation of the factory, but it's not used for planning and control of the manufacturing equipment. Then if you go to a digital twin, we have both. We have the automated data flow from the physical object and back from the digital object to the physical object. And only then we should call this a full digital twin. I think that's important. And I'm now in the rest of my talk, I'm really talking about the digital twin. So we have a data flow from the physical world to the digital world, and then back from the digital world to the physical world. Then if we see what can we do with that, it's a little bit detailing what I already said. So we have the automated bidirectional data exchange. Then an important point is also the real-time capabilities and high-fidelity virtual entity. That I have to explain a little bit because, of course, these terms are not absolute terms. What's real-time and what's high-fidelity? Real-time can be quite different depending on the purposes. But I think it's always something between microseconds or seconds. So it's not like we wait for hours or days for the feedback. But for some applications in the time order of seconds may be enough. But if I think, for instance, in the use case, I'll show you at the end of my talk a machine tool, which is actually controlled from the digital twin, which in that case is in an edge cloud of a factory. You really need a microsecond delay time, just a few single-digit microseconds from the digital twin to the real machine. So real time, very often microseconds, sometimes a little longer in the area and the domain of single-digit seconds. Then high fidelity is also that. Basically, it means the digital object or digital representation should contain all the information necessary to do the intended control of the physical object and to understand the physical object. But we have to be aware, digital representation is never a one-to-one representation of the physical object. Not all characteristics of the physical object are part of the digital object, just the ones we need, but all the ones we need should be part of the digital twin. Then if you look at what kind of models can be used, we have pretty much everything which is available can be part of the digital twin. So we have multi-physics representations, multi-physics modeling, we have multi-scale modeling, but not only physical representations. Of course, there has been a lot of research over the last 20 years, but recently we have these data-driven models which are used for machine learning and other AI applications. They're probabilistic and data-driven models and simulations. And all of this, of course, can be part of a digital twin. Then I already said we have the feedback to the physical modeling, to the physical system. And we use the digital twin for analysis, for monitoring and control, but also for prediction of the behavior of the real world physical object. So that's about what the digital twin is about. Okay, so that is a motivation and introduction. So we are all on the same page here. And now I'd look to possibilities to structure and organize digital twins. And I'd like to use here, I mean, there are different models, how to model a digital twin. I'd like to use here, and that's what we use mostly in our works, is 5-dimensional model, also developed by Tao. We look at, if you look at the center, we have at the bottom the physical entity and the virtual entity. I talked about that already a lot. But we also like to include services as part of the digital twin. So like if you look at a factory, those are like simple services, maintenance, provision of tools and other things which are necessary for the manufacturing process. But it could also be training and education for workers. So many services we can imagine for a factory. And if we want to have a full digital twin, these should also be modeled and part of the data model, which is used to represent the factory or the manufacturing system. And then if you look at the 5 dimensions, which are then included here, we have the physical system. And that, of course, includes a lot of sensors, actuators, and controllers. So the introduction of digital twins also needs and some changes on the manufacturing system side, on the physical entity. And it also allows new things to use actuators, controllers, which then are fed by data from the digital twin. Then the data model merges and processes all the related data from the physical, from the virtual, and from the service level. Services, we have rather standardized, now standard procedures with standardized encapsulated functions. And of course, there's the bi-directional data exchange, which I mentioned and talked already about. And then we have in the virtual entity, the digital representation of all the attributes of the physical entity and also of the services provided, like geometry, physical properties, but also behavior of the manufacturing system. So that is this 5-dimensional model of a digital twin. And if we look at what are difficulties, what are challenges, why it's so difficult to implement a digital twin in manufacturing, then there's several things to be considered. One is we still have a rapid evolution of the DT concept. So we implement a digital twin, follow everything which might be current state of the art, and then a year later already the new concept introduced new possibilities. So we still have a rapid evolution of the DT concept. So it's not possible to have one static digital twin which stays the same as long as the factory is operating, for instance. If you look, you mentioned I worked in the automotive industry a couple of years. So typical, so passenger car models now have a lifetime of 6-7 years. And during that time, the manufacturing system wouldn't change that much. I mean, there's continuous improvement of the manufacturing system always, but the basic layout doesn't change. But it doesn't mean that the digital twin can stay the same for 7 years, because after 7 years, it would be completely outdated with the rapid evolution of the DT concept, which we still have. So that, of course, is difficult to incorporate and difficult to follow. Then we still have a lack of standardized DT approaches. There are some, I'll talk about one, the AAS, in a second. But it's not like we have one worldwide accepted standard for digital twins, which everyone would be using. But there's a lot of developments have happened there in the past years. So I think we are proceeding there quite good. Then, of course, we have the domain dependency of the digital twin implementations. The way we need a digital twin depends on the domain. If I look in manufacturing and already within manufacturing, if I'm in the domain design, engineering design or civil engineering, then it differs for sure. But even a digital twin for, say, an automotive factory would be different from a digital twin for airplane production. Or if you look at medical technology. I use these two examples, aerospace and medical technology, because we all know that the requirements for documentation and for not changing any proven processes are even higher there than in automotive industry. So that also is reflected in the digital twin. Of course, it's also an opportunity to reflect it there and to do this there and make sure these requirements are met. But obviously, the digital twin itself will not be exactly the same. Then we have a lot of concerns about security. So data security, digital twin needs to really maintain its security and integrity. So anything which goes like if you have a digital twin driven factory and it would be possible for someone from outside to hack that digital twin, of course, it would be a big problem. So all these data security concerns have to be followed. Then we don't have like an agreed set of performance metrics for digital twins. There, of course, some performance indicators, some KPIs which are agreed on, but there's not a worldwide standardized performance metric for DTs. And then, of course, there's a last thing like technological dependency, or one could also just influenced by other rapidly evolving technologies. Example also related to the use case I'll show you later is communication technologies, with going from, if you look at a factory, maybe there was Wi-Fi used for a factory as long as communication technology was the 4G standard or LTE. Now we have 5G, and 5G actually is fast enough and reliable enough to use it for communication in a factory. There's also this possibility for the so-called campus network. So a company could have their own closed 5G network to transfer data in a factory. And of course, that has an influence on the way digital twins are implemented. And even though 5G still has some shortcomings, and in terms of real time, it's not quite as good as we would like it to be from a manufacturing point of view. Right now, the 6G standard is already under development, and we know once 6G is implemented and running, we can really use it to have a real-time control in a factory. And of course, then that changes the digital twin implementation. Okay, then what we use now, and I talked about lack of standards. There are a couple of standards already implemented and accepted worldwide. One is the AAS, or Asset Administration Shell, which is actually has been standardized to guarantee interoperability for autonomous systems and also AI applications, but mostly interoperability for autonomous systems. And we can use this also for standardized data exchange for digital twins and for the implementation of digital twins. AAS structures data, creates submodels in predefined ways with defined properties. So we have a standard to describe the assets and their properties as they're in the physical world, in the virtual, or in the information world. So AAS is one of the standards which are now implemented, which are very well suited to be also applied to digital twins. So let me come to an interim summary, because before I come to the second part of my talk, if you look at digital twins, there's a lot of research, interdisciplinary, extensive, with heterogeneous results on digital twins. We really have lived through the shift from the concept phase now to implementation phase and evaluation of digital twins, despite all the challenges which are still there. There are various use cases, and there's one difficulty. They're sometimes difficult to compare. because there's no single taxonomy for digital twin, which makes it difficult to compare the use cases in terms of performance. And that leads me to the first, say, new part or scientific part of my talk here. How can we classify DT applications? And then the second question will be, where's DT research heading in the future? And then I'll talk about the self-learning digital twins. Okay, let me go to the taxonomy. There are different ways to classify a digital twin. And what I propose, or we propose here from my group in Kaiserslautern, is to use these three areas, use what we call the level of the manufacturing system, to look at factory level, machine level, and process level. I'll elaborate that in a second a little more. We have developed this, actually, this classification as part of this corporate. It was mentioned I was at UC Davis for 1 year. We actually had a 9-year joint funded project on modeling for manufacturing systems with the partners TU Kaiserslautern and UC Davis and also UC Berkeley. And we developed this 3-level approach there, but the second way for classification is the scope of the application. Do we use the digital twin for analysis, pure analysis? Actually, that would still be just, you only need a digital shadow to do the analysis. But then if you want to use it for monitoring and control and for predicting the behavior of a manufacturing system, then we need a true digital twin. And then the type of models, that's one thing which really came up with a machine learning wave over the last 3, 4, 5 years now, to look at the white box models, which is a physics-based model where we have the physical understanding of what's happening in the manufacturing system. Then we have the pure black box models, which are really just the machine learning based on a lot of data, and then see the results. And then, of course, we have in between the gray box models, which try to combine both. Most prominently at the moment, it's these so-called PINs, the physics-informed neural networks, would also be kind of a gray box model, and they promise to combine the advantage of both the black box models, which are typically very fast, and the white box models, where we really understand why is the manufacturing system behaving that way it is behaving. So as I told you, I want to look a little bit in this distinction of the levels on the manufacturing system. So the factory level is infrastructure above the machine levels, like your material flow, the layout of the factory, also the information organization in the factory. And that, of course, is important for value creation through the machines and processes. So it's the overall factory layout. Then on the machine level, we look at the manufacturing equipment. So that's machines mostly, like very classical, like a machine tool from a milling center, or a machine for additive manufacturing, also a robotic system for handling could be here. And actually, this is probably the area where the implementation of digital twins is the most advanced in manufacturing, because every machine tool maker now has a digital model of the machine, and it's also prepared to have this bidirectional data exchange. And then if you go down to the process level, there are a lot of physical modelings like finite element or molecular dynamics models or discrete element models to model all these manufacturing processes, like a cutting process, a forming process, additive manufacturing process. Actually, we see a lot of research on this modeling and simulation at CIRP, at the conferences of our International Academy of Production Engineering. But to be honest, sometimes I think what we are lacking is the connection with the two upper levels, with the manufacturing equipment, the machines. There's already research on process-machine interaction, but it turns out it's not so easy to do that. But there's very little interaction then from the models of the machine or of the process up to what does it mean for the factory level, for the material flows, for the energy flows in the factory. So the idea, of course, for digital twin is then later on to also combine these, but we have to say the models are quite different on these three levels. On the factory level, to finish this topic, we have modeling and optimization of the entire production system with regards to efficiency, performance, cost effectiveness, also quality of the products coming out there, or of the energy efficiency if we have an issue coming from sustainability considerations. On the machine level, then we monitor and control the individual machines. And the process level, we really look at the manufacturing processes and try to optimize those. So that is one category for our taxonomy for the digital twin. The second is scope of application. That's more straightforward, maybe, because it's really we have the scope. Do we want to predict things like forecasting future events, for instance, machine wear, material needs, to enable preventive actions in the factory? Then we have the monitoring and control. So that's real-time tracking of production status. And then, of course, again, bidirectional data exchange, automated adjustment to ensure quality and efficiency. And then we have analysis, identifying and analyzing errors, quality problems in historical data and existing data, but also with a goal to improve process and product quality. So and then the third classification in this taxonomy is a type of model. Do we have a white box model using existing knowledge like physical laws to model a production process or a material flow? They offer transparency. We know what's going on there, and also deep understanding, but often take a very long calculation time. Then we have these new black box models, which are data driven. So we take data from the factory, analyze it, and by that make predictions about the behavior without really knowing why does the system behave that way. And the gray box models, as I already said, is a combination of both. And if you bring these three views together, level of the manufacturing system, scope of application, and model type, you kind of get this cube structure, three-dimensional structure, and then you can look at what does a typical or specific digital twin implementation do. It may be a gray box model on the machine level with the goal of doing maybe prediction and monitoring and control. Then you have two of these little cubes out of the large cube in the center, which would form the implementation of this digital twin. So we think this is a quite nice way to show then which of these parts, this is, of course, if you have all 3 by 3 by 3, so 27 little cubes implemented, that would be like the highest coverage of a digital twin. But it's not in all cases necessary to do that. So it's completely fine to have a digital twin implementation, which just does what is needed for the purpose. But then it should be clear what is not implemented when comparing it to another digital twin implementation. So that's our proposed taxonomy. And now let me go on to this part of self-improvement for digital twins in manufacturing and use the taxonomy already to look at ways for self-improving digital twins. If I look, why do we want to do this? Of course, and I think also in this Auto Twin project, I think I don't have to convince anyone that we have to do this. We have to continuously update digital twins. They have to be adaptable to changes in the operational environment, and also to do continuous improvements of the digital twin. The factory may have continuous improvement steps. Of course, they have to be reflected in the digital twin. And also, as technologies progress, it has to be possible to update the digital twin. One other way to do this, even without technology changes, is to maybe have initially the digital twin deployed based on a white box model, a physical model. Then it may be slower than we would like to have it. But then as the manufacturing system operates and continuously generates data, this data can be used to generate a black box, or then when combine the two, a gray box model, to improve the quality, for instance, of the predictions a digital twin can make by coming from a little slower physical model then to a fast gray box model, which can then make fast predictions for how will the real manufacturing system behave. So now this leaves the questions: how can a self-learning digital twin be integrated in a manufacturing system? And what learning capabilities are required on the different levels of a manufacturing system? And I'd like to talk a little bit here about supervised and unsupervised learning. That's now in relation to the black box models. And if you look where we are here then in the black box model, but then have scope of application, all three, and level of the manufacturing system, all three levels. And then if we do supervised learning, what does it mean? We need as input, we need labeled data. So we generate data from our factory with all the sensors in a factory. We have actually a lot of data coming from factories now, but very often it's not used the way it would be possible. And if we have supervised learning, we have to be able to label the data. Then we categorize it. Let's stick to this slide. In the three, for instance, categories, we can classify, do regression analysis, do classifications. And then we have unlabeled data coming into this process now. And the idea of supervised learning is once we did this with labeled data, it is possible also to predict the outputs for new unknown inputs, which are not labeled. If we go to the unsupervised learning, then we have completely unlabeled data, do all the clustering, the regression or anomaly detection, do all that without data labeling. Of course, if we have labeled data, this is easier to do. But if you have the unsupervised learning, we really have to find the patterns and correlations only in the data sets. So if you look at the process to do this, and this is I show you all the arrows already now. I think that's easier. So we start from one. Of course, we start for self-improving digital twin, which uses supervised and unsupervised learning, can also use reinforcement learning. We start from the physical entity, so from the real factory or manufacturing systems, we generate data through sensors and store that in the data model. So that's the second step. Then we have a data model, which is just generated from the data. So that's a black box model. But we can then provide services for the factory, like maintenance, for instance, from the black box model. Then we can validate that in the virtual entity and try to generate more understanding what's going on there, and give, again, store data, and then give feedback to the physical systems, do adjustments in the physical system. So that would be one concept for self-learning digital twin with a pure black box model. Now, if we go to the gray box model, this means in our taxonomy, this entire thing shifts one. We look at the cube like a center of the cube, and have the implementation of the potential of gray box model. Then we may start with white box model based services. We may have a physical representation of our factory to do predictions there. We store the data from the white box model. And from that, we develop a black box model based services, which again are used as services. And then, of course, we can combine the white box model-based services and the black box model-based services to have gray box model-based services. And then they are, of course, again, then used to predict the behavior of the physical entity, to control the physical entity, and also to analyze its behavior. Okay, with these two approaches, now I'd like to go on to my use case as the last thing I would like to look at and show you how we implemented not all of these, say conceptual ideas, but quite a few of them already. We have a hybrid digital twin for a CNC machine tool. You see that on the lower left part. It's actually a machine tool with a open source Unix-based CNC. This was the only way for us to really develop it and implement things the way we wanted to, because the commercial CNC controller providers at the moment, some things are changing now, but when we started this project, we're not so open to these changes into their machine tool controls. But this is a 3-axis milling machine. And you see there like the milling tool and the main spindle there and some of the kinematics. Then we have services there, monitoring and control of that machine. Actually, this machine is controlled via a 5G network to the virtual entity. It's not done by cables. In our applications, this is done by 5G. So that's why I said I know now what we can do. We can make simple geometries. 5G is fast enough with the latency. If geometries get more complex with a lot of freeform sculptured surfaces, then actually 5G doesn't have the speed we need, but we know already we're in a pre-project for standardization of 6G telecommunication standard. And we know already that once 6G will be implemented, that's still a couple of years, but not too many years. We're talking about 4 years maybe for the first implementation. Then will be really possible to replace the cables in a factory and in a machine, to have the digital twin, the representation of the entire machine, of the kinematics, of the drives in the machine tool, in the cloud, and then really send the CNC code or for the PLCs back to the machine. But of course, to do this, we need a high quality digital twin of the machine tool. And we are working already on that. And this is a hybrid digital twin using both physical models, but also learning from the milling center itself and to take data. So use the existing data, which is stored in the data model, then to improve the predictions and also the machine tool control in the virtual entity. We use as a standard to transfer the data. It's done with OPC UA. I think most of you know that. But it's not done via cable, but via a 6G implementing that now. There we are more the benchmark for the new implementation, but existing with a 5G connection. And if you look at this hybrid digital twin a little more, so our initial situation was we had a digital twin at the machine level. So if you think back of the taxonomy, that's just talking about the machine tool. Integrated connectivity to the machine control unit. It monitors the status and enables control of the machine. It's based on I just don't say not only kinematic models, but also taking into account like the mass and acceleration as a result of masses. And so I say a kinetic model, which is a white box model. And we have connectivity via 5G and OPC UA between the virtual and the physical entity. And improvements, what we did there is we have additional sensors. So we have now wireless sensors in the machine tool. And then the data goes directly to the data model, which improves our possibilities to do analysis, monitoring, and control, and also prediction of the behavior of the machine. We have data-driven insights using historical data for the machine to train the model and to continuously improve it. But also we have still the physical models, obviously, of the machine tool. It wouldn't actually make any sense to throw away this available physical model, physical knowledge of physics-based knowledge on how the machine performs, and to do everything just data-driven. So we already have a hybrid model here implemented. Okay, that brings me to a summary, and then I'm open for your questions and discussion. What I did in the last 45 minutes gave you an overview of what we here in Kaiserslautern think about or think is the implementation if we talk about digital twin framework and implementation in manufacturing systems. And we are proposing, did this already, a couple of publications on this is taxonomy, and the approach for self-improving digital twins is to use for black box models, self-learning and unsupervised learning, but also to use the physical knowledge about the machines which is available to come to a hybrid or gray box model. And last thing, I showed you this use case, our hybrid digital twin for a CSC machine tool. So with that, I'd like to thank you for listening now for 40 minutes. And now I'm open for a discussion and your questions.
Thank you, Professor Aurich. Thank you a lot. Very nice talk. And let's see if, okay, there is a first question on WeChat from Nicola Cialini. Nicola Cialini asks if you experience a digital twin implementation in small and medium enterprises.
Well, that is an important question also, not only for digital twin, around this entire topic of digitalization for SMEs. I would say, so we had some experiences with that, with also doing digital twins for SMEs. But it depends very much on the kind of small, medium-sized enterprise where you go to. It's I think for say like a traditional manufacturing company which has been doing excellent machines for a long time, it's very difficult right now to really be fast enough in implementing these things. But also like a startup company, I also would see as a SME, and they're very good in implementing digital processes and digital twins. But for the like traditional mechanical engineering companies, it's very difficult. They very often don't have the people they need with the knowledge to implement that. So they have to look for outside help to really implement things. So I would say it's possible, but it's not easy for a traditional mechanical engineering company to do this.
Yes, totally agree. And also after implementation, there is the maintenance. They don't have the expertise to maintain these digital twins.
Yeah, to maintain so it is difficult, but I think it's important for them to do this and to also at least hire some people who have the knowledge to do this, to do at least the maintenance. The implementation and design of the digital twin can be done with outside help. I think for the maintenance, you need at least some inside knowledge. So it really means a little bit of a change in the personnel structure of the, say, established, long-time successful SMEs.
Yes. There is a long question from Yavar, so I do invite Yavar to pose the question by talking. Otherwise, it's too long.
Thank you. Thank you, Professor Mata. Thank you for the very nice talk. I actually got very inspired by your talk. Well, I would like to talk more about have your opinion on the gray box models. So specifically, the kind of architecture that you propose is, I think, for the gray box is a combination of the white box and black box models. However, we also have like physics-informed neural networks that you mentioned. But those systems, now if we want to like create like an end-to-end like physics-informed model like that, for many cases, those systems are for continuous systems, originally developed for continuous systems. Manufacturing systems are in general discrete. I don't know if you have like encountered this kind of problems in your research, or you have any solutions in this regard.
Yeah, so first of all, I totally agree with what you said. So the pins,
Yes,
I subsumed them as a gray box model, but they come more from the machine learning domain, of course. I think they're useful on the process level. We have a lot like these continuous models, like finite element simulation of a cutting process or discrete element simulation in case of additive manufacturing. Then the pin makes a lot of sense. And it's right, like if you go to the factory level, we have discrete event modeling.
exactly.
Um, and it's a lot more difficult to integrate this. So the physical informed neural networks, the pins are not really the best way to go there. And there, so I think it's more difficult, and they're not such like established. The pins are new, but we know their work. Approaches to make gray box models there, because also the behavior, it's not so much physical. If I have the discrete event simulation of a factory, I mean, there are tools for that, um, but they are not very much physics based. So I think we actually did some things to combine with Siemens plant simulation to do some physical parameters as part of the discrete event simulation. And I think that's a step towards having a gray box model there, but we're not as far as on the process level.
I see. Thank you very much for the clarification and Nasdaq.
Time we receive other questions. I have a list of questions, so I will start. Okay. Just the first, your opinion, the 5G, what application do you think will make it possible? Will be more at process level to control, I don't know, the laser process, the machining, or more at, let me say, product manufacturing system level?
Um, Probably it's first on the manufacturing system level, because there the real-time requirement is not that strict as on the process level. On the factory level, I mean, real time is talking if I can react in the material flow within, say, half a second or a quarter of a second, that's fast enough. And that 5G can already do.
Mm.
On the machining level, I mean, the long-term vision really is here to move a lot of the intelligence from the machine tool to the edge cloud of the factory, and then to connect it via 5G or 6G in the future, and say just leave the PLCs in the machine and have the CNC being a virtual entity in the edge cloud. But
Yeah.
that's still a vision. I wouldn't say that we really have that. That's a goal, but I think probably if you look at a time frame of 5 years, that's possible to do. And that will have a real impact on the way machine tools are made, the control of a factory is made, how many do you have the CNC, how much intelligence is in the CNC at the machine tool, and what is in the cloud. And of course, why do I want to move this to the cloud? It's all these other things. Data analysis is a lot easier if this is all in the cloud. Then I have all the data there, and I can start to do analysis of the data and improvement a lot easier than when everything is contained in a local CNC.
Yeah, I agree. And what is, in your opinion, the right way to build a benchmark for digital twins? You know, if you want to show how a digital twin is performing well or not, okay, how can we build a benchmark, our community?
Oh, that I think that's a difficult one, because, as I said, they're so domain dependent, and of course, people only implement what they need
Yeah.
and not more. And then it's very difficult to benchmark that against each other. So that would be something maybe we can do also at SERP or in other institutions, to really come up with a standardized
Or
benchmark, which maybe doesn't cover everything, but covers the main application areas.
yeah, this I think is a question for our community. And then I have another question on the Tau model. Okay. In the Tau model, you know, you have shown the bottom left, the physical system, right? Okay. In
Yeah,
your
yeah.
interpretation, is really the physical system, or is the model that we know of the physical system. So the digital twin helps to describe the physical system. So as we have more data, we understand more the physical entity.
So here, now we have it, right? This you talked about.
Yes, we understand more and more the physical entity. Okay. And so that node, because many, I think, misunderstand that node. In your opinion, is real the physical system providing the data, or is the model that the digital twin builds on the physical intel system, and then it will update more and more with the data?
Oh, the question is whether the data goes directly from the system, like the sensors, to the virtual entity, or via the data model.
Yeah, but the physical entity here in
Yeah.
that model is real the physical entity, or is the model of the physical entity that the digital twin builds? You know, it's a production line. I know that there are 5 machines, and I don't have a model of the transporters, for instance. And then with the data, I understand that there is one AGV, for instance. Okay. And then I add this information in the model of the physical entity. Because otherwise, it's not a model. It's just a physical entity. So what is your
Yeah, I think it's more the model, but the question is very difficult one. If you look at the machine tool, as you said, so I mean, the machine tool itself has also a lot of digital components. And then we have discussed this a lot. Is this part of the real world factory, or is this part of the digital twin? And that's sometimes, I think, not really clear. So probably it's correct to say we have the data. That's why the data model is in between. It's actually even more, that's a question I have discussed a lot with colleagues. If you go on the factory level, then it's the ERP system. So you have the ERP system with all the material flow data and which the workpiece goes where and is assembled when. So that's what's in your ERP system. Is the ERP system part of the digital twin, or is it part of the factory? I think that's actually a difficult question. Now, most people say actually it's part of the factory, because without the data, you cannot operate the factory. And then the virtual entity would actually operate on the data model and not on the real physical entity.
Okay, it's not an easy question, but we can discuss even in the future about this. We also had internal discussions on this.
But it's a very interesting question. We have discussed this a lot. So I felt most people thought like the ERP system, we have discussed it with that example, but I think it's the same kind of thinking with your question. And I think most people I talked with wanted to see that as part of the physical entity, even though I personally think maybe, but it's entirely digital. So it could also be part of the virtual entity.
Yeah. Okay, so thank you a lot. I can only claim from here like this since we are virtual. Thank you for your talk. I think we don't have any other questions. Generally, our talks have a restricted duration of 1 hour. Thank you again, and if you are available, we can send you some results of AutoTwin project in order to receive the feedback.
Yeah, sure, that'd be great. I'd be interested in that. And also thank you for giving me the opportunity to hold the talk here. It was fun to do and also fun discussion. Thank you.
Okay. Thank you again, and thank you to the audience.
Yeah, bye-bye.
Bye.
Bye.